Well, here we are, back again. Right back where we left off a minute ago. Talking about... Oh, hey. Back here. There you are. Trying to get this thing to come up on the slideshow. There we go. So, target cell specificity. And covered a bunch of this already along the way. I thought that was more appropriate to learn about what a target cell is before we started talking about all that other stuff. So, but just to reiterate, target cells are target cells for a particular hormone because they have those specific receptors that the hormone binds to with complementary shapes. So the ACTH receptors are only found on certain cells of the adrenal cortex. So ACTH, there's another abbreviation. What does that stand for? Adrenocorticotropic hormone. So adrenocorticotropic hormone. So the H means it's a hormone, chemical signal. Tropic hormone means that it's coming from another gland. The message is coming from another gland, the hormonal stimulus. And it's going to have its target cells in the adrenal cortex only. So although the anterior pituitary releases ACTH and it goes everywhere in the body, it only has the effect on certain cells of the adrenal cortex because that's the only cells that have the receptor. Whereas thyroxine, which is another name for thyroid hormone, receptors are found nearly on all cells of the body. So that's the thyroid hormone helps regulate metabolic activity, and most cells are responsive to that hormone. So target cell activation. How does the cell know to receive the message? Well, here's three factors. Blood levels of the hormone. So is the level of the hormone in the blood high or low? Oftentimes it doesn't have to be real high to have a big effect because of all the amplification that can take place. Another aspect is the number of receptors on or in a target cell. So if, let's say, the blood levels of a hormone are too high, that's like the shouting, hey, you don't need to yell. Or if the blood hormone levels are too low, hey, speak up, I can hardly hear you. So that is if you want to make the analogy between person-to-person communication, blood levels of the hormone are like the speaking level of whoever's talking to you. Whereas a relative number of receptors in or on a target cell are more like how well you hear or receive the message. So it might be where you can't hear. And so it's like me, I'm old, so I have to tell somebody sometimes, hey, Sonny, can you speak up? I can't hear you. Or maybe somebody like my dad sometimes, his hearing aid gets turned up too loud. So we want to have both of these be just right. We want the level of hormone, the signal to come in loud and clear, but not too high, not too low. And we want the target cell to have the right level of receptiveness, not too little, not too much. And another one that goes sort of in between 1 and 2 here is the affinity of the binding between receptor and hormone. How well do the shape of the hormone and the receptor complement each other? In a perfect world, they would fit just perfect, but that doesn't always happen, does it? So the amount of hormone circulating in the blood can influence a number of receptors. So if the hormone levels are chronically lower than they should be, the target cell might make more receptors so that it can hear the message better. It might downregulate. If target cells are, they might lose receptors. They might not make as many in response to chronically high hormone levels. This is, I haven't thought of a really good analogy for the other one, upregulation, but downregulation is kind of like nagging. Nagging. Like my wife nags me constantly. I tell her, look, I told you I was going to do that. You don't have to tell me every 6 months. I'm just kidding. First of all, my wife never nags, or very rarely, and I do a lot of stuff around here. But imagine, you kind of, if somebody's constantly going, yeah, at you, eventually you become desensitized to it. And that's kind of what happens with a cell sometimes. And this could be a particular issue with chronically high insulin levels and a type of diabetes, which we'll discuss a bit later. So hormones circulate in the blood, either free or bound. I've talked to you about that already. The water-soluble hormones, the hydrophilic ones, they just circulate around by themselves. Or if they're hydrophobic, then they are bound to a carrier membrane of some kind or another. That would be the steroid-based and the thyroid hormone attached to some kind of plasma protein to act as an escort or a carrier. The concentration, the blood levels of the hormone have a trade-off between how fast they're released and how fast they're inactivated. So how much hormone we find in the body is a interaction between how much is released, how fast it's released, and how quickly it's removed from the body. Now, I might add that this also has applications to pharmacology, that the concentration of circulating medications reflects how fast it's being put into the body by whatever mode, pill, patch, intravenous, and how fast the medicine is deactivated by the body. So this section here, even though it's endocrinology, this concept is also transferable to pharmacology. And how do medicines and hormones, how are they removed from the body? How are they taken out of circulation? Well, sometimes they're deactivated by enzymes. They're degraded. Think back to acetylcholinesterase. Acetylcholinesterase, which helped. Oh, wow. What a big piece of farm equipment driving by. Acetylcholine, that's hard to ignore. Big, huge John Deere tractor. Acetylcholinesterase helped turn the signal off between the neuron and the muscle. So this is a common theme as well with hormones. They can be removed from circulation by the kidneys. Some are, some aren't. They can be broken down by the liver. And with the case of medication, sometimes they can be metabolized by a cell. So the half-life, hopefully you learned about half-life a little bit in A&P1, is the time required for the level of hormone in the blood or medication to decrease by half. This concept was first discovered in the 1600s by Sir Isaac Newton, who was looking at how boiling water cooled off. And here you see my wonderful artwork. It's actually pretty good as far as my artwork goes. It turns out that this is called the classic decay curve. It applies to how water cools when you boil it and let it cool off. If you put something in the refrigerator to cool off, it has to do with radioactive decay, radioactive isotopes. It has to do with hormones and hormone levels in the blood. It also has to do with medications in the body. So this classic decay curve has wide-ranging implications, and it plots the amount remaining versus time. So the amount remaining, I got percent remaining here. We're going to start at 100% on the y-axis and go down to 0. Both axes have 0 as their origin. And then on the x-axis, we're going to have time in half-lives, the number of time it takes to degrade by half. Now notice what I just did. I just showed you, before I started talking about this graph, I told you a little bit about it. I described what each axis was. And this is important when you find yourself in a position to give presentations to people, whether it's in person or online, and you're going to show some graphic information. Always describe the axes first. Otherwise, your audience is not going to know what the heck you're talking about. They're going to be looking at this graph trying to figure it out, what the axes mean. You're going to be talking about what's going on in here. And you might say, well, I hope I never have to do that. I don't like speaking in public. And a lot of people don't. And the thing is that those of you who go on to become really good at what you do, you're going to end up becoming trainers, and you're going to get tapped to train other people to be as good just like you. And so for the best of you, that's going to be in your future. So there's a little bit of tidbit there. All right, so half-life, the time required for a level of hormone or medication or radioactive isotope to decrease by half. I guess I should have done that with my laser pointer. So by definition, after one half-life, we start out with 100%. After the first half-life, we're gonna go down to 50. After the second half-life, we're gonna be not the other half, but half of that. So half of 50% is gonna take us down to 25%. In the third half-life, it's going to be another half of this 25%, down to about 12.5%. And after about 6 or 7, certainly by 8 half-lives, it's pretty much gone. Now you might say, well, what is the half-life? How long is it? It depends. It depends on what it is. And for hormones, anywhere from a fraction of a minute to a week. For radioactive isotopes, it could be anywhere from milliseconds in some of these isotopes that are built in particle accelerators, to some radioactive isotopes of uranium have a half-life of a billion, that's with a B, billion years. So it's case specific. Each substance has its own characteristic half-life. Same thing with medication. Some of them are cleared through the body really quickly, and some of them linger for a while. So the more familiar you can get yourself with this decay curve, when you get to pharmacology, hopefully you do, then you'll be better off. Response times. Some hormones respond immediately. The response is immediate and quick, like the adrenal medulla hormones. Some, especially the steroid molecules, could take hours or days, or like estrogen and testosterone. So with the endocrine system, these then also have their effects from anywhere they last a few seconds, like maybe adrenaline, to several hours. And you can see that this is widely variable. Sometimes the effects disappear really quickly. Sometimes they persist for hours. Once again, it's very vague, I understand, but it's a complicated thing, maintaining homeostasis. Here's a table that will compare and contrast some of the things that I've just been talking to you about. And so that's in the book. You can go back and look at that. That's a good study guide to help frame your understanding. So when we have this one here is interactions. How interaction is when two or more things get together. What happens? So we have 3 of them. I don't know why the third one should be on this page. I wonder if I can do that real quick. I can't do that from here. Watch this. Now let's pull you down here so we can see you all on the same page. There we go. So here we have 2 or more hormones working together. What happens? There's a couple of outcomes. One, the first is where one hormone can't work unless it has another one present. So this means that one hormone basically needs to have the permission of another in order to work. So for instance, the reproductive hormones, testosterone and estrogen, they need a thyroid hormone to have their effect. So somebody with chronically low thyroid hormone levels might have issues with what the reproductive hormones are supposed to do. Synergism, that's a business buzzword. Synergy, the whole is greater than the sum of its parts. That means that the effect of one plus the effect of another is amplified, so that you have an interaction term. So where this is where 1 plus 1 equals 3, where you get 1 plus 1 equals 2, but then you get an interaction, and that makes it a larger effect. So for instance, glucagon and epinephrine both cause the liver to release glucose. So epinephrine, we know that is released in the fight or flight, And you don't know about glucagon yet. I haven't talked to you about it, but it's a pancreatic hormone that causes the release of glucose. So when you release them both, they work together, and that gives us more fuel to run away from those angry bears. And the opposite of synergism, antagonism, where one or more hormones they're opposite. They're opposite of each other. They send things in different directions. Insulin and glucagon, the two pancreatic hormones, are like that. All right, so let's cut this one off, and we'll come back and do the hypothalamus in the next section.